tonight's presentation, once again, going to ask Karl to come up. He's all wired.
With you about, I grew up in Coulee City, and Wenatchee was the big town. Wenatchee was where we went to shop, especially at Christmas or before school. And I parked down here on Wenatchee Ave tonight, and this is a pretty place. It's neat to be back, and neat to be back in the winter, although it feels odd with this warm, snowless winter. Okay, let me get set. I had a good joke for you, but I'm at the age where I can't remember good jokes now. It's neat. I should say to you that it's wonderful to present in person tonight. I presented a talk very, very similar to this to the Puget Sound group just over Zoom. And it was Zoom that pushed me toward retirement from Central. And then when I gave that talk, I was reminded why I no longer wanted to teach, and I've made the right choice. And but presenting in person is awesome when the technology works, of course. Well, welcome. And tonight I want to talk about Foster Creek and Foster Coulee, places that you may not have heard much about, or places you may not have been to.
Okay, my program
in the past, and I want to try to tie
give you lunch.
Foster Creek and Foster Coulee to glaciers, to Ice Age floods, and to glacial lakes. Early geologists first recognized that Foster Coulee and Foster Creek were somewhat unique because they were, first of all, near Grand Coulee and Moses Coulee. And let me back up a second. They were unique because of a combination, thank you, a combination of features. Number one, they were near the Grand Coulee and Moses Coulee. Number two, the orientation was different, and especially for East Foster Coulee and East Foster Creek. Third, they were in an area once covered by a large glacier, an ice sheet, essentially. And fourth, they're now mantled by sediments. And so it's that combination that leads then to these key questions. Did glaciers and huge floods shape this area? Makes sense, given their location. How are Foster Coulee and the Foster Creek valleys related to the Grand Coulee and Moses Coulee? What's the relationship of these to Pleistocene lakes? I'll define Pleistocene in just a bit. And how have they evolved to present? So I'm going to focus on Ice Age, but I'm going to take you to present with a couple projects that my graduate students did during my career at Central. So my background, essentially, I've spent much of my lifetime, especially my early life, on the Columbia Plain. Like I said, I grew up in Coulee City, and I used to travel through this area, right by these features on the way to play the Brewster Bears or the Bridgeport Mustangs. We'd drive right by this, and I probably didn't notice it then, but later in life I did. And so I've been around this for a long time. And secondly, I've been researching it, collecting data here for 30 years. And a lot of that research was with students. And so you're going to see just a little tiny bit of work by two of my grad students. I had a couple undergraduate students who did good work out here. And then almost every year, I would have students out here in one part of that watershed or another, including one year we had a field school out here. So I've spent a lot of time there, and I try to give a lot of credit to the students because over my career, for those of you who have taught, you often learn more from your students than they learn from you, it seems like. And that was, I think, the case there. So where is this? And I'm going to take you through about 5 slides here, 4 or 5 slides, something like that. And let me just help you get your bearings. Here's Wenatchee. You're going to see that dot on several of these slides. And we are in the northern part. Where we're going tonight is the northern part of what I call, and what Don Meining called, the Columbia Plain. You might call it the Columbia Plateau or the Columbia Basin. Okay? We're also on the north end of the channeled scablands. So the channeled scablands, as many of you likely know, are our classic areas of ice age flood erosion, and they're indicated by all these dark tendrils, these dark pathways through this landscape. And we're up on the north end of that area. We're on the Waterville Plateau. Again, here's Wenatchee, and we're on the north end of the Waterville Plateau. And on that north end, you can see I've outlined the 3 forks of our drainage, and here's Bridgeport to help you get your bearings. And as you look at that, just start thinking about why this pattern on this wonderful Google Earth image. What is it about these blonde squares? You start thinking about farmland. This is dryland agriculture country. But look at all this area that doesn't have those squares on it as well. So patterns start to show up at this scale on Google Earth. Yep, there we go. So, and let me back up just to make sure. Okay, we're good. So some observations, some kind of, now you've got a spatial groundwork here, or you've got an understanding of where we are. Let's think about what's there on this landscape. And I've made a very, very simple geology cross section to show you what's underfoot in that area. The lowest material are old, what we'll call Cretaceous granitics. These are granite and metamorphic rocks like gneiss. These are old, 90 million year old stuff. 90-ish million years old stuff. And then over the top of that, there's basalt. And let me take a quick time out and step back. We'll see in parts of the watershed, this granite and gneiss is exposed, but mostly basalt is exposed if there's bedrock. Above that, there is Pleistocene, meaning roughly the last 2.6 million years to about 11,000 years. Pleistocene glacial outwash, which is deposited by meltwater, and till, just deposited by glaciers. Okay. Over the top of that, there's glacial lake sediments. And over the top of that, there's post-Pleistocene, so more recent, loess, which is windblown sediment. Okay, so I've thrown a lot at you already. Just think in terms of, we go from 90 million up here to, we'll round it off and say 15 million year old basalt. And then we've got really recent geologic time sediments that are glacial in origin, lake in origin, and windblown in origin. Okay? So now we'll put some names on these drainages. West Foster Creek, right over here on the west side of the drainage. In the middle is Middle Foster Creek, and to the east, East Foster Creek. And the upper part of it is known as Foster Coulee. And that's what often grabs people's attention. They hear this word coulee. So what's a coulee? For those of you who haven't thought about this much, let's define it. So a coulee is often a dry drainage, a dry canyon, we'll say, and it came about from large discharges of meltwater, floods, from lakes that were near glaciers. We call those proglacial lakes. What they are, when you get on the ground, what you see is they have steep walls and they're often pretty flat floored. They're not pool table flat, but they're often fairly level in their floors. So what are the famous coulees you've heard of? Grand Coulee. Come on. Zach, I think I lost it. Sorry. Think about Grand Coulee, and there's an upper and a lower, right? Frenchman Coulee. Did I hear somebody say that? Moses Coulee. What are we missing? Lind Coulee, yeah. And Lind is kind of a sad coulee in a lot of ways. I mean, it's kind of like Foster Coulee in a sense. We good? There we go. So I've pointed out, I didn't point out Lind, Steve. I avoided that one, but I pointed out upper, lower, Moses right here, and then Frenchman, and the one we missed that's really pretty popular is Potholes Coulee. And we could keep going, but what I wanted to draw your attention to, these are some famous coulees. I didn't list Foster. It's remote. It's hard to get to. It's private land, but we can get into little pieces of it. And this is one of those pieces. So I say it's subtle. Here's the walls of the coulee. They're not much more than 100 feet high, whereas the upper Grand Coulee is, I think the west wall is 700 feet high. You know, this is not as majestic, but nonetheless important to understanding the flood stories. And this arrow is showing, and on each successive slide here, the arrow is showing the way water flowed here at one point. And later I'm going to show you that flow reversed here. Here's lower East Foster Creek Valley. So now we're getting down closer to Bridgeport. Looks very different. And now you can see, it's hard to see bedrock. You've got to go clear back here to see that basalt. But look how the rest of this looks just kind of soft, like there's sediment over it. This is blanketed by sediment. Here's West Foster Creek Valley. So now we're over in that western part of the drainage. This is the Bridgeport Hill Road, and water has flowed down that over time and continues to. I forgot to mention, all three of those branches have current streams in them, but they're tiny. You could step across most of them with one big step. And then here's Middle Foster Creek Valley. Again, pretty mantled by debris, but here's basalt up closer to the skyline. So you get a little sense of that material. And the other thing I forgot to mention on that observation slide is all these slides, with the exception of that, really remind us this is a dry place. 10, maybe 12 inches of precipitation a year on average. They're breaking that this fall. They're out of there. I'll bet these folks have doubled their precipitation out here this fall if they're anything like Ellensburg, where I live, or Wenatchee. So a wet time now, but this is a dry place, a semi-arid environment. Okay, so I've laid out the drainage. Now, one other thing to think about, look at the proximity to the Grand Coulee and to Moses, and also to the Columbia River Valley here. Our place sits right in the midst of those. Okay, so in that position, if you look at my star indicating the approximate location of Foster Creek, you can see that this was an area that was shaped by the Okanagan lobe of the Cordilleran ice sheet. That's what the blue is. So it shows it as this overall Cordilleran ice sheet. There were a number of lobes, including the Puget, the Purcell Trench lobe over here. We're dialed in on the Okanagan lobe. And the important thing with that is that glaciers often mask or erase landscapes. In other words, what's happened in the past is often masked by glacial debris, or it's scoured away by that moving ice. Okay? This area has been looked at, it's been mapped clear back into the 30s and really before. This is J. Harlan Bretz, a person that you folks are probably very familiar with the Ice Age flood story. Brett started work out here by the early 1920s. Actually, I think he was even in here a little bit before that, but he began his work there in the channeled scablands by the early 20s. This map came out in 1932. He maps the boundary of this area, and right up there, kind of hidden behind the zoom stuff, is kind of the center of our study area. Okay, so the early player here, J. Harlan Bretz, the early student of this area, was looking at this area too, but not in the detail that he did elsewhere. Okay, so now let's get to the meat of things. How do we interpret or what's happened on this landscape over time? What are some interpretations? And what I'm going to do is I'm going to throw out some of the things that other geologists and geographers have laid out over time, and I'll give you a little piece of evidence for each of the things that they are arguing for. And I want to emphasize most of this is not my work, it's the work of others. Later on, I'll bring in some of my stuff. So Brett started this, he was looking at this earlier. A Yale geologist named Richard Foster Flint came along in 1935 and he mapped our drainage. He mapped especially prominently the East Foster Creek, and he said that coulee cutting dates back to an earlier ice occupancy, meaning that what he's arguing for is that there was more than one glaciation out here. There were several. We've not found evidence for that yet, but it makes sense given what's happened on the other lobes of the Cordilleran ice sheet. So the evidence should be there, but we've not seen it. Whoop, I keep pointing the wrong way, you guys. There we go. So some of you may have Bruce Bjornstad and Gene Keever's, one of their books on Ice Age trails, essentially their road trips, there's hiking trails, etc. They're wonderful books. And essentially, they've argued over time, as have some others, that Foster Creek flowed from east to west. And it did so because the elevation in the east is about 2,100 feet, and to the west, it's about 800 feet. And water flows downhill, right? But they also argued, here's where things get a little bit more twisted. They said, hey, East Foster Creek started east of where the Upper Grand Coulee is. So now in your minds go, okay, think about it. You've been to Steamboat Rock State Park and you see that giant coulee, And they want to say that water flowed from a Waterville Plateau that was larger. It extended east of the Upper Grand Coulee. And so I put this X here showing that there was no coulee there then. And so that's something to think about. Did that water that flowed from east to west did it start over on what I call the Heartline Hill? And did it move all the way across? We know water now flows downhill in this, and it makes sense that it did in the past, but where did it start? Later, or more recently, Richard Waite, a USGS geologist, has said, nah, he can't make it work to have a stream channel connect from here to there because of elevations. That stream has to flow uphill essentially. And so he's argued, yeah, water's flowed downhill there, but it started west of the Upper Grand Coulee. And again, he's going to say that before the Upper Grand Coulee was here, there was a small creek here that he calls Coulee Creek, and it picked up some of these small drainages and it flowed to the south, kind of like the Upper Grand Coulee does today, but it's just a small drainage. And later, Ice Age flooding and spilling over of glacial Lake Columbia turns this into a coulee. We'll get there in a minute. But so here's where Waite starts that. So you've got, on this part of the story, you've got several people who have argued over time that that creek was flowing to the west. And then along comes Larry Hansen in the 1970s, and he says, hey, this was flowing to the west, but it was picking up floodwaters from glacial Lake Columbia. And this is a lake you may not have heard of in the past. I'll bet you've all heard of glacial Lake Missoula, but glacial Lake Columbia formed behind this Okanagan lobe. The glaciers do wonderful jobs of blocking drainages. And so that river valley was blocked off and the water ponded behind it, and it flowed out over that surface, and it made that dark surface that I alerted you to earlier. It created a scabland. It scoured that surface and it sent water down that drainage because there was still no Upper Grand Coulee. This is hard to wrap your mind around. No Upper Grand Coulee, my God, where would I swim? I mean, you think about Banks Lake and that wonderful reservoir that sits in there now. Where would you paddle a kayak? That's all gone. So instead, water is flowing over the top of the plateau into the Foster Creek drainage. And this is one possible path to deliver water to Moses Coulee. This is the dilemma. If, you know, we all have our things, right? We all have things that we're interested in and maybe over interested in. And one of the things that geologists and geographers have been hung up on for years is, how do you get water into Moses Coulee? Because there's no direct channel path. There's no clean channel leading right down into Moses Coulee, right past Jameson Lake, where Jameson is now. There's no path to get water into there cleanly. This is one possibility. And it may be the path is not clear because it's been covered up with glacial debris. It's been mantled by debris. So that glacial Lake Columbia, I've already shown it to you. Here it is in a little different geometry, but there it sits up there. And I just wanted you to see this map to appreciate Glacial Lake Columbia was pretty good size. It extended beyond Spokane to the east and extended up on the Rathdrum Prairie to the north. Okay, so what's the evidence for lots of water coming from Glacial Lake Columbia, perhaps as a flood, as floods, really sluicing down in there? And let me just back up just for a second. Glacial Lake Columbia, when it filled up and spilled, it would have been a flood of its own. But now combine that with Glacial Lake Missoula here, when it spilled down, it rolled right into Glacial Lake Columbia. It would have made bigger floods. Floods that came through Wenatchee early on before the glacier was here. Floods that came through Wenatchee later when the glacier had retreated. But when that glacier was there, that would have sent floods out across the plateau. And so what's the evidence for that? On East Foster Creek, one of the things that just grabs you is this is a great big channel with a little tiny current stream. And we call that an overfit valley. The valley's too big for the stream. This is the stream right now, and again, you could step across that. The other thing that argues for flooding is these are pretty classic scablands, scoured basalt, and look at the lack of farmland out here. That's often a good indicator that there's no soil to farm in, no soil to speak of. And this area is mostly scabland. So that's good evidence. But the but here is, where do you see giant flood bars and giant current ripples? Let me show you if you're not familiar with those. Here's little tiny Wilson Creek east of Soap Lake. These wrinkles, see those lines? Those wrinkles are giant current ripples. And giant current ripples tell you floodwaters have come through an area. The bigger the ripple, the wider space they are, the faster the floods. And the taller the ripple, the faster the floods. This is a big flood bar that those are formed on. This was deposited by floodwater, and the bigger the bar, the bigger the flood. So I don't see those when I look at aerial photographs and Google Earth for the Foster Creek drainage. I don't see that stuff. And so that has me scratching my head. And tonight I wanted to be honest with you guys. I don't have all the answers yet as I have researched this. How many more years do I have to research it as well, right? I'm 30 years into it, and I better get rolling on this. So the other question here, if I'm throwing questions at you, is why does the coulee end at Leahy Junction? If you've driven Highway 17 over the plateau and you get to the junction with Highway 174, that'll take you to Grand Coulee, 17 takes you to Bridgeport. Right in there, in that vicinity, the coulee really ends. And the maps and now I just say it's a creek valley. It takes on a different form. So a question. Okay, so now if we have that position of the ice lobe change a little bit, and this could still be as the ice is advancing, but it's changed a little bit in its morphology. Now, instead of blocking the Columbia River Valley over here, we're blocking it near Brewster or Bridgeport. Let's see, that's Bridgeport, so near Brewster. If that happened, could that send water up this valley? That's what some folks have argued, and it makes sense. If you have an ice dam, a little bit later, I'm going to talk about lakes here that sent water up in this valley and held it as a lake. We could argue that here too. And so Richard Waite, who I mentioned earlier, has said, hey, if that ice dam sat there long enough and if it was high enough, that could push water clear back, and that could help essentially erode a Grand Coulee, an upper Grand Coulee. It could send, in other words, and there may have been a coulee here by then, but there wasn't a coulee up here yet, or that water would have been spilling into it. So if you have a coulee partially eroded, could you send water in? Or the plot thickens, could you instead send water into Moses Coulee? So here's another way that you could get water to Moses Coulee. The problem again with this that we've wrestled with for years is where's the valley that delivers that water? Things don't line up real well, and they're not clear. There's not a clear pathway in. Okay, so now let's have the glacier grow to the south. In other words, it advances to the south. We've moved from up here, we've advanced south, and now we're at Withrow. And this is the Withrow moraine right there. And see how the land use changes on that? It's real dark. Much of that's too rocky and steep to farm. The really great farmland's going to be mostly down in here to the south, and pretty marginal stuff up in a lot of this. That glacier advanced to the south, and I just wanted to throw some numbers at you. In the northern part, where that crossed the Columbia River, that ice was over 1,600 feet thick. So what's that, a quarter of a mile, third of a mile, something like that? That's impressive. And at the snout, here on the moraine, it's still over 700 feet thick. That glacier reached its terminus at about 15,000 years ago, we'll say, ballpark number. Okay. Now, what if water is moving beneath the ice in tunnels, and this happens a lot with ice sheets? What happens if there's a lot of water moving subglacially and it comes down and it essentially flows and does weird stuff like flows uphill because it's under pressure? And this has been shown in other places. It shows it's flowing in what are called tunnel valleys. And those tunnel valleys, it's been argued by Joel Gombeyer and Jerome Lessman, they've argued that that is the likely source for Moses Coulee water. That you can deliver water there, and you can make the argument better with water flowing uphill through a channel network and reaching the head of Moses Coulee. And so this is, I don't know if it's stirred up the geological community, or the geographical community all that much, but it should, because it gets us thinking beyond Missoula floods to now Okanagan floods for Moses Coulee, a different source of water. Oh, come on. There we go. Okay, so now let's retreat, and I'm taking you now toward lakes. The ice is now retreated. Remember, we reached the maximum at about 15,000 years ago, ballpark, and the ice is retreated, and now again, there's water ponding behind it. And so let's start talking about that ponded water as lakes. I could have done it earlier, but with the ice advancing, I don't think any of that lake evidence survived. This did because the glacier is retreating, and so there's been no glacier to scour it or mask it. Okay, so we call that lake that formed Glacial Lake Foster. And the question is, did it once form as one lake? I think it did. And it, in backing up water, it essentially sent water over the edge of the upper Grand Coulee into now a glacial Lake Columbia in the upper Grand Coulee. And we know that happened fairly recently because there are deltas in Banks Lake that tell us that water was flowing off the edge of East Foster Coulee and depositing that. And if you go just south, there's another one at Horse Lake Coulee. And that had to happen when that lake level was high at about 2,100 feet. So water, we know at times that water flowed from west to east. It dumped into an excavated upper Grand Coulee, which is right here, and left that really prominent landform. And if you stand on Steamboat Rock and you look across the way, there's Foster Coulee, and there's that big delta. Pretty awesome. Okay, so now we're back, we're in Foster Coulee, and I pointed out that the glacier advanced and retreated. Here's glacial outwash, that's meltwater deposited. And here's glacial lake sediments. And what's weird about this is it looks like basalt is sitting on top of it. It's not, it's just, this is a basalt valley, and these sediments were deposited in that valley. So an outwash plain often forms out in front of glacial ice. And on the Waterville Plateau, there's not a real distinct outwash plain that formed by the Withrow moraine. And even as the ice retreated to the north, there's not a clear-cut, big, huge, thick sequence of this outwash, but we see little slices of it like that. Okay, so now let's focus on these glacial lake sediments. Back in 1893, I.C. Russell, another early geologist, identified these as glacial lake sediments. These, what he called this fine white silt and clay. This stuff, and think about that, fine light silt and clay. Think about how erodible that stuff is. It's soft, it's easy to erode by wind and water. And he nailed it. He said, hey, there was a lake here, and it was after the ice invasion. So what's the evidence for that lake other than that soft white silt and clay? If you're going, how else can you tell this is lake sediment? And actually, let's back up. Why would a lake have fine silt and clay in it? It's suspended from sediment carried in. If you've seen glacial lakes, you've often seen they'll look kind of blue or kind of murky. Or if you've seen rivers that are draining from glaciers, they're carrying a lot of sediment. In the still water of a lake, there's the finest sediment, the silts and clays. They're deposited out last, and those deposits blanketed the lake floor. But then after that, there's erosion of those easily eroded sediments. Those sediments are carried away. They're carried downstream or they're carried downwind, in this case downstream. And so I'm trying to argue here with this image that there was erosion all around this thing around this remnant of lake floor. And I don't know if it looks like it to you, but that's like a bench or a table. It's a fairly level surface. That's a terrace. And we're going to call that essentially a fill terrace. It was made by a lot of sediment laid down by lakes, and then a bunch of it eroded away. If you look at this now on what's called a LiDAR image, look at the terraces. Those smooth areas are those benches. And this is just downstream of where I just was. So there's terraces in this drainage that suggest, and they're made up of glacial lake sediments. They suggest that that material was laid down by lake action. Better yet, this is where things really get cool. Remember, I showed you those deltas, or the delta in Banks, in what is now Banks Lake, the upper Grand Coulee. There's big deltas out here in this watershed, especially on the East Fork. You're looking at that, looks like a bench to you, but that's right at the mouth of the channel. It's a delta. Let me show you this in an overhead view. That's it. That V-shaped feature formed from this meltwater channel right here. And these are not made out of lake sediment, they're made out of sand and gravel. This one is so big and prominent that Washington DOT has been mining gravel out of it for years. It's huge. It's right on Highway 174. And then here's another one for you to see. I've mapped like, I think 15 or 20 of these in the drainage. And what's neat about them is you can get elevation information off them to see how deep the lake was. And in fact, that's where we're going here. So how deep was this lake in places? It varied on the part of the watershed you're in. But if we go to this terrace remnant, this isn't a delta, it's a flat-topped feature composed of lake sediment, and it's at about 1860 feet. And if we go up to the high shoreline where there's a delta, it's at 2150. So that lake, if I did the numbers right, that's almost 300 feet deep there. A temporary glacier, or what we might argue is temporary, a short-lived glacial lake sitting here that was close to 300 feet deep. And it was loaded with sediment if all that white stuff was laid down by it. There we go. Okay, so now if we get up close to that white sediment, here's what it looks like. There's bands, light and dark bands. And we call those we call them couplets because you go light, dark, light, dark, light, dark. And you could more accurately call them varves that formed each year. So a white and dark couplet forms each year. And this is on my list to do. And my wife was saying that she wanted to travel and do all this stuff in retirement, and I want to count varves instead. And this, what I need to do is take a big ladder out with me. There we go. And these hills are begging to have their varves counted. And the yellow lines that I put down give you a sense of, I ought to be able to clear these slopes, and I know the landowner, and I think I'm going to be good there, to just clear a little path like I did back here with a shovel, set a ladder up, and try to count the way down. And what that will give you is a sense of how long the lake sat there. It's going to be a minimum estimate. I'm not going to get all the varves, but I'm going to get a sense of it. And my bet is we're looking at a lake that was several hundred years in existence. It should have been around a while. Okay. So the other thing is over time with students, we tried to date these features, mostly deltas. And we tried to find the high shoreline, and then we would sample sediments, and we're doing it in a pretty high-tech method called OSL, or optically stimulated luminescence. Don't worry about the details there, but essentially it's a way to date sediments when you don't have organic matter. You can't do radiocarbon dating, for example. So this delta north of the Chalk Hills, where I've just been showing you this stuff, is almost 16,000 years old, according to OSL dating. If it was one date, I'd go, who knows? But over time, here's what we've gathered. So essentially, this delta near Leahy Junction, 15,000, 16,000 here, and Upper Deep Creek. There's the one we were just at. This one here. So we've got 4 good delta dates that are all high 14s to low 16s, somewhere in there. This one is not a delta, but I'm pretty comfortable with that. And so you get a sense of the age of this. And if you're going, well, wait a minute, if you're thinking back earlier, that glacier was supposed to be at its terminus at 15,000. And I'm showing stuff that's a little older even. You got to keep in mind, these dating methods are pretty coarse. These get you in the ballpark, but when they say 790, there's about 14,790, there's about 1,000-year error bar on that. So I'm happy with the way these bunched up. In honesty tonight, I wanted to show you that life is not always so simple for field research. You spend a lot more money and you get dates that don't make any sense. That's the yellow ones. I don't know what the heck's going on there and up here. And it's just, and this is a place I so wanted to get a good date. I went back, hiked in there twice. But things aren't always as clear as you'd like. Okay, so now thinking about the West Fork, there's some wonderful stuff here, and I'll bring you back here right at the end as well. This is a neat drainage. This is a side drainage to the West Fork. It's called Smith Draw. And let me back up. Remember the 2,100 feet was that high level that sent water into the upper Grand Coulee. We're a lot lower here at 1,750 feet. But we still have lake sediments. They're down on the bottom. There's what I should have put a question mark here. I'm not convinced now this is Tiller outwash, but there's lake sediments low. But check this out, you guys. There's 2 glacier peak layers, glacier peak tephra, essentially ash, from an eruption about 13,000 years ago. And then up near the top, there's a real prominent Mount Mazama tephra, which is from the eruption that made Crater Lake. And I do have some in here, some clams and snails that we dated at about 7,900 years. What's odd is my early interpretation of that is that those were lake sediments, and I don't think that is the same lake. I don't think that's the Ice Age lake now. We're very recent in time. There must have been maybe a wet meadow that got a lot of water flowing into it seasonally. I'm still scratching my head at this. And that one below. So take those with a grain of salt, but down below Glacier Peak tephra, we're in Glacial Lake Foster. So here's another place. There's some work that I need to do kind of cleaning this up as well. Okay, so that glacial lake uh, persisted, and I've labeled it here, and it got smaller with time as the ice retreated. And as floods came down the Columbia, late floods, they would have sent water, high energy water, up into that valley, and they would have left sand and gravel now that now after erosion shows up as prominent terraces. There's your flat top, and then steep side, another flat top, another flat top. And now let me show you that in reality. And we're looking back up the drainage. That's that prominent flat top. But what's different here is these aren't made out of lake sediment. They're not deltas. They're made out of sand and gravel, but they're not delta landforms. They're essentially terraces. And so I think these formed from water circulating back up into the drainage and laying down sand and gravel in that lake, but in a flood fashion. This is a real problem. These are textbook terraces, but they don't fit the pattern of lake. But they do tell us high energy. Okay, so now let's shift gears and come to the post-glacial period and wrap this up talking about what's happened more recently. And so we're back in the chalk hills in the central, or the kind of the western part of East Foster Creek drainage, that we're in the lower part. And these hills that I've shown you now several times make what we call badland topography. And I would argue that this is Washington's. I'm going to go one more slide forward, and then I'll come back. Come on. There we go. This is Washington's examples of the kind of stuff that you can see at Badlands National Park. It's just not as exciting because it's not as widespread and it doesn't have these different colors of sediment, but they form the same way. It's fine textured sediment that's highly erodible. We talked about that early on. So if you've traveled and been to Badlands or maybe Death Valley where there's badland topography as well, you've seen this stuff. That badland topography shows up as these little islands, essentially. And imagine at one time, this was all filled with sediment. And this stuff on the green area has eroded away. Here's those islands. There. Okay, so now if you move into let's move real recently in time and think about, it's 1965 and you're in Douglas County and farmers were still trying to farm in between those islands. And that is a tough thing to do. Here's the islands we were just looking at. Over here. That's a hard thing to do because these sediments are so erodible. They blow when they're disturbed by farming, and they erode by water as well. By 2011, and I chose 2011 because this is a good image, this was all put into Conservation Reserve Program. So, and the reason they did this, the reason the USDA worked with farmers to do that was because these soils are so erodible, they're sending sediment down this drainage and into the Columbia. And I don't think the Columbia is the big deal, but it's just anything, if you've got wildlife down below here that depend on clean water, they're not getting it in that highly erodible area. So this was put into Conservation Reserve probably in the 80s, And in my mind, it's been pretty successful. What else has been done here because of erosion? Well, this is a road from the 60s. I think if we went back to the 1960s air photos, we probably see this was the Bridgeport Hill Road. And you can see there's a sudden drop off from that into the channel of the East Fork here. So erosion has been common here. And you can see the highly erodible nature. This is the Middle Fork. And this is just a place that is susceptible to erosion. So the USDA and farmers have wrestled with how do you deal with this? Conservation reserve programs are one way to deal with it. We'll get back to another solution in a minute. This is a slide I've shown for years in my classes. I'm just blown away by this. This is on Smith Draw. This was the farmhouse. This was a farm granary. It made no sense, even to a Scandinavian farmer like my ancestors were. It would make no sense to have those separated by a steep-walled channel. And so in talking with farm families up here, this drainage was incised in 1948. By a year like this is shaping up right now, but I think it was more May and June precipitation, just a very wet spring, and that caused head cutting. That caused this channel to move up valley, eroding back into here and creating this, what I call an arroyo, you might just call it a gully. So it really a classic. And one of my grad students, Paul Blanton, looked at this drainage and tried to map when the incision happened. And he was doing it with old aerial photographs, essentially, at different years. A wonderful master's thesis. The other way that, in this case, I think it was Fish and Wildlife and maybe DOT has tried to deal with erosion is they've done these big structures. And this is one of them. There's a couple in this drainage. They put a lot of money into this to stop the head cutting. So when you put in a structure like this, it should stop the drainage from cutting any further than this back into the big meadows here in this West Fork. What's happening, that's kind of old school. What's happening now is that Foster Creek Conservation District and Fish and Wildlife they're putting in little structures like beaver dam analogs where they pound in posts and they put branches and things on them to simulate a beaver dam. And what you're seeing here, I didn't have good photos of this, but one of my grad students, my last grad student, Griffin Hansen, was looking at the effectiveness essentially of these, and there's a beaver dam analog right down in here. And Foster Creek and Fish and Wildlife have put a bunch into this drainage. What they're trying to do is collect sediment to stop the incision. If you collect sediment, you're no longer cutting down, you're filling up. And that's been the effort here. And again, it all goes back to old lake sediments that are so easily eroded. Okay, so now just think about as we pull this together, this Foster Creek Valley system has been around since really pre-last glacial times. It's been around a while. So it's been around more than 15,000 years, more than 20,000 years. Maybe it's 100,000 years. We don't know yet. We know that all those valleys were covered by the Okanagan lobe at least once. We know that East Foster Creek, I've shown you evidence it's flowed east and it's flown west. We know that it held at least one lake, probably more. those lakes were big enough to build large deltas and to deposit thick varve sequences. They were around a while. And I've got enough evidence to say that, hey, those were around about 16,000 optically stimulated luminescence years ago, which don't match up with the other dating method used to date the moraine. But we know it came after because there's no glacial till on top of this. And now, finally, we know that those glacial lake sediments have resulted in land use and management changes. And that's neat. As a geographer, I love all this stuff, but ultimately it's also fun to make this tie to human activity as well, recent human activity. So with that, thank you. Thanks for hanging in there with me. I hope it didn't go too long. I'm happy to answer any questions you've got, or I'll try to answer any questions. Thanks.
We have a question and answer microphone right here. Somebody deliver. Here you go. Anybody questions?
Three examples of landslides as a result of an unstable slope once the glacier retreated.
In this drainage, there's landslides definitely, and they're old, but not, I don't know that I could say I've seen any evidence here of landslides that I think are post-glacial in the sediments. You can sure see them along the edge of the Columbia from east of Bridgeport on the Columbia River Valley all the way down here to the Wenatchee area. Answering your question, down to the Chelan area, we'll say there should be evidence of post-glacial landslides as the glacier retreated. But in that drainage, I can't say that I've seen what I thought were caused by losing the strength of that ice, right? Good question. There's definitely landslides.
Can you talk about Burton Canyon that comes in right at the south end of Jameson Lake?
Yeah. What would you like me to talk about?
Well, it's got
The fact that it's rough, that road is rough as heck. The last time I drove there.
seems kind of like the uppermost part of Moses Coulee, that it just like it came from nowhere, and yet it's pretty deep.
Yeah. A couple of years ago, I led a field trip out there and we looked at the head of Burton Draw. It'd be west of St. Andrews, if you know where that's at, and north of Highway 2. And that drainage kind of comes out of nowhere and it develops pretty quickly into a prominent drainage. And that may be something that picked up water that flowed from it would be from that model I showed you where it came from kind of the Grand Coulee area and flowed along there. But there's no channel leading from the Grand Coulee area all the way to that area I just referred to. The channel does just kind of start there right along. I can show you on a map. I forget, Heritage Road, I think it is. And it kind of comes out of nowhere, but there's not a lot of high terrain between there and Grand Coulee. So you could have had floodwaters come there, but there's no prominent channel getting there. Neat place. And I explored that, I think it was 2 years ago, and I was scratching my head on that too. It's coming in from the east. So yeah, good question.
Any, is this on?
Yeah.
Any comments on why we're seeing incision all of a sudden happening mid-20th century?
Uh, yeah, good. So the question is, why do we see incision mid and probably earlier as well? Is it tied to land use? It's kind of an age-old question. What makes arroyos? Is it land use? A lot of times the argument is grazing, overgrazing leads to arroyo incision. Over farming should as well. If you're doing conventional tillage, there's more runoff on that than there is on we'll say conservation tillage now. But why in the 40s, for example, at Smith Draw, I think there it was tied to the precipitation events. If Paul, I'd have to look back at Paul Blanton's thesis a little more, but if he's showing it in other times, I would fall back to my land use arguments there, I think. But often triggered by some, is it a rain on snow event or a thunderstorm? I think those play a role as well when you don't have the vegetation cover. Yeah.
I don't know the cultivation history well enough. Does it make sense for there to be a change in land cover or land use 1930s, 1940s and not 1870s or 1880s? Why wasn't that gully there when that granary was built?
Yeah. Yeah, good question. I'm trying to think that Paul could only go back in time to the extent of air photos. And so we had 1939 air photos that limited us. And then he looked at newspaper clippings as well to try to get a sense of big erosion events that may have made the news. But why wasn't the gully there in the 1850s or 70s? I don't think there was grazing there. I don't know that there was farming there. I think it would be closer to 1900. But still, even that, why hadn't head cutting proceeded up there? I don't know. That's a good question. There's definitely been erosion and deposition episodes because naturally there were beavers in that drainage. They were probably trapped out during the kind of fur trapping area. And so that would have helped fill back in some channelization. And that was a wet meadow up there. But if I talk anymore, I'm going to go in circles. So yeah, that's a good question. Yeah.
You showed that you did a date sampling on Deep Creek.
Yeah.
And the Chelan Douglas Land Trust owns 1,400 acres, and it's the headwaters of 3 forks of Deep Creek.
Yes.
And each of those are abrupt spring-fed headwaters.
Uh-huh.
And this is our second year of putting beaver dam analogs on
Nice.
some of those forks. But I'm very curious about the spring-fed nature and why it flowed due north. There's a dramatic elevation change to get down to the East Fork of Foster Creek.
Yeah. So I don't know why, I don't know what it is about the geology there that's driving that spring-fed nature. I sampled up in there. It'd be kind of on the west side of that drainage, west head of that drainage. My guess is it's interbeds, sedimentary interbeds between the basalts that are providing the water, but I don't know the specifics of that. It's really, it begs the question, why do you have water flowing in the East Fork, Middle Fork, and the West Fork too? It's a pretty dry place, right, to have flowing water, and they all flow, I think, perennially, although small. So I'm going to stick with my interbeds, sedimentary layers between basalts. Yeah.
Higher northwest, the Clark Fork River outside of Missoula.
Yeah. Yeah, yeah, yeah. And this fit right in that, and that didn't surprise me. We couldn't have, with Paul's work, we couldn't have gotten it right to 1948 without talking with the farmers, and that's what they took us back to, that very wet year. Yeah. Any other questions tonight? Yes, come at it again.
Stepping back a bit further in time, you're looking for some way to divert water up east along the East Fork of Foster Creek.
Yeah.
And the elevations are a little bit challenging, but what are the possibility of alpine ice coming down the Methow to Pateros and blocking the Columbia there?
I know Richard Waite did his dissertation up that drainage. I can't remember how far he had alpine ice coming down. I don't think that alpine ice, by the time it made it to Pateros, if it did, would be near the elevation that the Cordilleran ice sheet would be to create a deep lake that could come up that drainage.
We don't need Cordilleran ice sheet elevations, I don't think.
You say we don't need
Don't
them?
need to get up to Cordilleran ice west of Pateros, got up to 4,000 feet or so. I don't think
Okay.
you need that much ice to divert flow up East Foster Creek.
So you're saying after the ice had retreated or before?
No, the best example is probably Lake Chelan, but if you work any place around the North Cascades and north, you know, the story we learn about is of the Cordilleran ice sheet. And the distribution of erratics says ice from the north, but the landscape is an alpine glacial landscape, orange and U-shaped valleys. And for example, the Lake Chelan Trough is clearly a big fjord carved by ice coming down the valley.
Yeah.
And that fjord extends further to the southeast than the flow of ice during the last glaciation. That is, at the
Okay.
bottom end of the fjord, ice was flowing up the trough.
Right. Okay.
So I think there's clearly an evidence for an earlier history, call it Evans Creek, 23,000
Yeah.
or older than that, of alpine glaciation that you wouldn't expect to find necessarily a drift record of, but there's
Gotcha.
a landform record.
Yeah, I hadn't even considered that. Good.
Well, okay, there's a little channel that if you're at Pateros, look across the Columbia to the southeast, there's a channel behind the hill that has
Yes. Yeah.
bothered me for a long,
Yes,
long
I
time.
know that channel. Yeah.
Why?
Yeah. 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 I always assumed it was floodwaters that created that down on one of the early floods, but yeah. Other questions? You got me thinking, Ralph. When do you plan to start the work at the Chalk Hills, and do I need any help? Oh boy. I was trying to get it going this fall, and this fall turned out wet. I was trying to get out there in early November, so probably March, early April, somewhere in there. What about the water flowing over the glacier to these channels? There can be certainly water flowing over ice rather than beneath ice, and in addition to water out front of the glacier. So yeah, that's a possibility. Yeah, so anything else? Hey, I'll hang around if you have questions. Thanks again for coming tonight, and it's been fun. So take care.
Thank you for watching tonight's Wenatchee Valley Erratics meeting minutes and live presentation by Karl Lillquist. Our next meeting and presentation is scheduled for February 10, 2026. Until then, all of us here at the Wenatchee Valley Erratics wish each and every one of you a very Merry Christmas and Happy New Year.